Hello.
Hey,
How are you doing?
I'm doing good. How are you?
Not too bad, not too bad. All right, so we're doing some pre-calc. What are we doing today? We still doing exponents and logs or
Yeah, so we actually haven't had a math class since the last time we met, which was I think like Monday.
okay.
We had a kind of crazy week with like SOLs, then we had a field trip with like a college professor. Anyway, it was just kind of a weird week, so we haven't done anything else.
Okay. Yeah, so let me so if I remember you looked pretty good with logs. Um then we were doing some exponent stuff, is that correct?
Mm-hmm. And I'd probably just want to just go over everything, just be safe, because I don't really remember all the rules and
Mm-hmm. Yeah, so
properties, I
actually
should
let's
say.
see what you remember. So what are our exponent rules?
Um, I know there's kind of like the product rule, like the quotient rule, and
Yep.
stuff like that. But
Yep, and you don't have to remember the
power,
exact names, but do you remember like what the math is? Because if you can recall these, you're
yes.
good.
See if like for the power rule, it's like x to the we'll choose like fifth, and then you do like a five out here. It would become x to the 10th.
Uh, I think I just want to double. Okay, so you're close. If it's like 5 to the power of everything, so it's x to the 5, all that to the 5. It's actually
Mm-hmm.
multiplied, not added.
Okay.
So this is equal to x to the 25th. But yeah, so
Okay.
that's the power rule, or the yeah, power rule, or power of a power, whatever you want to call it. What other rules do we have?
Hold on, I think there's like music or something playing. Let me turn that off.
Yep, no worries.
All right, so that wasn't even me. It was some golfers behind my house.
Oh, gotcha.
Yep. I was like, what's because I'm home alone right now, so I'm like, what's playing?
Yeah.
But all right.
So there's one with
The product
addition.
rule is like, yeah, it's like if two values with exponents multiply, they become addition.
Yeah. And the key word is they have to be the same base.
Mm-hmm.
So ax plus y. Yep, absolutely. And there's another one that's very similar. Do you remember what that one is?
Yeah, the division becomes subtraction.
Yep. So I'm just gonna write that like this. Yep, exactly. Okay. So what else do we have?
Um, there's like the power of I think it's called power of a product.
Mm-hmm. And what does that tell
But it's
us?
like if you have it would it's basically like what I did before with the x to the 5 and then the 5 equals 25
Okay. Um,
because so you have like a to the x times y would equal a to the xy because you said multiply them together.
yep. Yep. So this is like the power rule. Um,
Mm-hmm.
the the power of a product is it's kind of similar. Um, But the key idea is that we have two different like bases to the same power.
Mm-hmm.
And then how can we separate this?
It would become a to the x and then b to the x.
Like that, right?
Yeah.
Yep, exactly. And then there's another one for division, but instead it's a divided by b to the x is equal to a to the x over bx. And it's basically it. Um, yeah, that's basically all our rules. There's another one actually that I don't think we've talked about, called the fractional exponent rule. So if we have like a to the 2/3, is there another way we can write this?
Um, yeah, I'm assuming you mean like some type of uh, cube root.
Mm-hmm. Yep.
So it become like the cube root of 9 squared.
Yeah, exactly. Yep, and that may help us or not, but it's really easy if like maybe, and actually so this I meant to make this an A, but you know, 9 is the same idea. Maybe if instead of
Mm-hmm.
A is like a square root of something, then we can like get rid of the square root. So sometimes that helps us out. Okay. Yep, so that's all of our rules. What about our log rules? What can you remember off the top of your head?
So they're kind of like the same names, but
They do have
um,
similar names.
so if you have um, like log of the base times I guess like xy, it just equals both like logs of the same bases and then x plus y. So it's like
Yep.
log base x plus log base y.
Yep, and I'll choose B as the base.
And it's the same thing for division. It's log base x minus log base y.
Yep. Yep, exactly.
And there is a property, I don't remember what it's called, but you take the exponent and move it out into the front.
Mm-hmm. Yeah. That is called actually, yeah, okay.
Is
It's
it
called the
just like
power
the
rule.
power rule?
Yeah. I actually I don't even really remember if I like knew that it actually had a name. I just always like remembered it was something you could do. But yeah, yeah, power rules. So
Mm-hmm.
we can take log b x to the y and turn this into y times log b to the x. What else do we have?
Um, I don't know any of the other ones.
Yeah. Um, there aren't really many that are like widely applicable. Um, we've used in the past a property where we have b to the power of a log of the same base. This is just equal to x, like the logs and the b cancel. Do you remember this?
Yeah, because you could do like
Usually,
random fractions to make it kind of like work out.
yeah. Oh yeah, yeah. We did like log base 2/27.
Mm-hmm.
Yeah, I remember that. Yeah, most commonly this will show up as e to the natural log of x. Once you get to calculus,
Mm-hmm.
you'll see this a lot. And then this is just x here, because these are the same base, basically. So that's one other property. Another property that we haven't used yet, I don't think, is called the change of base rule. And this one is kind of weird. So I want to make sure I get this right. Um, yeah, okay. So if we have a log of base A and there's just a number, we can turn this into log of B over log of A and some other base. So we can literally just choose any base in the world.
Huh.
Yeah, it's very interesting. But sometimes this is very helpful to us to get logs like this because for the most part, whenever we've been doing you know math with logs, they've always had the same base because all of our properties have they'll need to be the same base in order for it to work.
Mhm.
So sometimes converting like this, like I think so far this is really the only way we have of like changing the base without like drastically changing the number. So I don't think we've come across any problems like this, but this property is definitely useful. Okay, so that's that. So that's all of our rules. That's good. Um, some more baseline stuff. Do you have these written down, or do you like know where to find them?
Yeah, can't you just Google like log properties and you find them?
Yep, that's basically what I do. I don't have these memorized either. So I wouldn't expect you need to. I don't know if your exams, if you expect to be given like a formula sheet or not. Um,
No clue.
yeah. Okay. Well, let's go on to the next thing. So now we're going to our graphing calculators. Okay. So if I have just a normal graph, what does e to the x kind of look like? Just good old fashioned y equals e to the x.
Um, yeah, I don't remember.
Okay. Um, oops, excuse me. All right. So, let me ask you this: what numbers are? Well, actually, yeah. So let's go ahead and choose to graph some. So, what would be e to the zero? Because e zero is usually really easy.
So that would just be like y equals 1.
Yeah. Yep. So this is our one. So this is our first point. And what can we say as x gets larger? We're kind of using our
Um,
limits here.
y would get larger.
Yeah, really large. And particularly, it gets large really fast.
Because it's exponents.
Yep. So that's basically how I'm going to draw it. It just goes up really fast. Not exactly perfectly drawn, but whatever. Okay, now what about as x goes in the negative direction? What's happening to the y values?
I guess smaller.
Smaller, yeah. Um, but just so we're on the same track, what do you exactly mean by smaller? Like, is it going towards negative infinity? Is it going to the x-axis? What do you mean exactly by getting smaller?
To negative infinity.
Okay. So, well, actually, let's test it. So let's see e to the negative 100. So this can be written. So what can this also be written as if it's to the negative 100? If we
Uh,
have x to the negative 1, how else could we write it?
Negative x.
Nope. It's like 1 over x.
Oh, okay.
Yeah. So what about
So
for negative 100?
100 over e.
1 over e to the 100. So the negative basically makes us flip it over.
Mm-hmm.
But so what's interesting about this number is it's not negative.
So it goes closer and closer to 0?
Exactly. Yep. So it gets really close, but never touches. So this is kind of like how e to the x looks. Okay. So that's the general shape. Now let's contrast that with y equal to the natural log of x. How does this look? What do you remember the natural log of x looking like?
So I'm assuming that it would be a vertical asymptote then.
There is. Yep.
So it
And
would
at
probably
where?
be it would intersect at 1 probably.
Mm-hmm.
And then I guess it would be like this. Or wait.
You're on the right track.
No, it would go down.
Very good. We'll go down. Now what about the positive?
Would it be at like going to 1?
It won't be going to 1.
Oh wait. It's across the it's like these two are reflected over y equals x, right?
Yeah, kind
Or
of.
am I
Yeah, actually they might be. Yeah, they might be exactly. I've never actually. Yeah, they do kind of look like that. They probably are. Yeah, they probably are reflected over the x one y equals x.
so this would just go to oh, I didn't mean an arrow. Hold on.
Mm-hmm.
Let's press this. Oh, that just selected a lot of stuff I didn't want it to. Okay. All right. This would just go to infinity, I guess.
Yeah.
I mean, I don't really know how to draw that on this, but
Yeah, that's okay. So you are right. It is going to go to infinity, but kind of in the opposite way. So this one goes even steeper to infinity. The natural log goes ever shallower to infinity. So it gets flatter and flatter as time goes on. But yeah, we're basically going to have vertical asymptote, as you said. So that's the idea. That's what these graphs look like. Um, and the base, if instead of e to the x or natural log of x, this is like whatever 8 to the x, and this is log base 8 of x. All that's really changing is kind of like how steep it is. So it's still going to be
mm-hmm.
1, but it's going to be like up here, for 8. It's going to be way up higher. And then for the log of 8, it's just going to be way shallower. So yeah, I think you're right. I think it is reflected across. That's pretty cool. Okay.
I was gonna say it looks like it was. All the points are kind of matching up.
Yeah. Okay, so that's that. So that's kind of. Oh, there's something. Have you talked about half-life, like exponential decay in your exponents and logs?
Um, no.
Okay. We might do a little bit of that. It's not too hard. Um, it's very similar to what we've been doing. Um, let me look at. Yeah, okay, we did this last time. So let me know what you think of this. Um, so I'm ready to introduce you to some new stuff. So I think you got the idea of like exponents and logs. Would you like to do some more practice, or are you ready to see a little bit of new stuff?
Sure, we can do some new stuff.
Okay. So we're gonna do half-lives. So do you just happen to know what a half-life is?
No.
Okay. So the half-life is used in chemistry, and it's basically the half-life is the time it takes for a substance to exponentially decay to half its original quantity. So, like, if we have, a chunk of uranium or whatever, it's kind of just decaying by radiation.
Mm-hmm.
And once it reaches half its original mass, we say that amount of time is its half-life.
So it's similar to like an LD50.
LD50, maybe. What is an LD50?
It's like how much of a substance it takes to kill like 50% of the population. So it's like an
Oh,
LD50 for itself almost. So it's like the time it takes for it to kind of like get rid of 50% of itself.
yeah. Okay, and I'm actually seeing. Yeah, yeah, yeah. So the LD graph kind of looks like this, right? Where it's basically you have 0 and then the population.
I can't see if you're making a graph.
Oh, you can't see it. Okay. Refresh real quick. That usually fixes it. I'll refresh too.
All right, I can see it now.
Yeah, so it's kind of like we have, 0 of the population and the population ceiling.
Mm-hmm.
Yeah. So yeah,
So it's like the point in the middle.
yep. And that's like, here or something. Yeah. So it's kind of similar. So we're talking about half-life. But in particular, it's an exponential function or like a log if we're trying to find the time. Um, so the one just a second, I'll make sure I got this right. Okay, yeah. So there's two components to half-life. So there's the exponential decay, which I kind of gave with the example of uranium. Decays to half its original mass. That's the half-life.
Mm.
But there's the other side of exponential growth. So maybe instead of uranium, we have bacteria, and it doubles every whatever amount of time. And then basically, once it doubles its size, that's kind of like a half-life basically. So imagine that we had a population of bacteria that doubles every hour. So this is one of our piece of information. And let's say that it starts with 10 bacteria. So usually we denote the starting as A0 equals 10. Um, what will be, well, so I'm going to ask you this. It shouldn't be too hard if you able to do this in your head. What is the population at 2 hours at t equals 2?
Starting at 10,
Yep,
40.
right. So it's basically we have 10 times 2 times 2. Yeah. So, but what if instead we had, t equals k? Is there a way we can write like a function that will graph the bacteria growth?
Um, in like Desmos,
Sure.
you could
Um, but you could also just write out the function. You don't have to graph it.
so you could do like y equals 10 times 2 times any letter and then put it on a slider so you can see it like go.
Hmm. Okay. I like your idea, but it's not going to be 2 times like k.
Mm-hmm.
Um, so for example, if we were doing t equals 4, it would be times 2 times 2 times 2 times 2, right? Because t when t was 2, it was just these two, and
Mm-hmm.
then t3, and then t4. So I'll give you a hint. It's an exponential. What is this if we had a base of 2?
Um, to the what is it? To the fourth.
Yep. So at y of 4, it's going to be 10 times 2 to the 4. Now if we have y of, oops, not y of k, 10 times 2 to the k. And um, that is the idea. Um, Hold on just a second. Okay. So this is kind of the idea here, but this actually isn't quite perfect. Wait, no, no, yeah, that's right. Yeah, this works. Um, now, but when we're talking about like the exponential decay of like elements, they don't follow like 2, like they don't double or they don't half or whatever. They follow e. So um basically all that is means is good to change for us is that um if we have some substance, so we have a0 is going to be equal to, oh wait, no, a0 times e to the kt, and then is equal to y basically. So let me grab an example of half-life. This is our problem. So the half-life of carbon is 5,730 years. So express the amount of carbon remaining as a function of time. So give you a little bit of help because we aren't given a starting amount of carbon.
Mm-hmm.
So we know that the continuous growth formula is I'm going to say like the final amount of substance. So I'm going to say AF is equal to the start times e to the kt.
So it's the y value,
What's the y value?
the 5,730.
That's not the y value. That's the t value
Or
because
that's.
it's in t.
Mm-hmm.
Or it's in time. It's in years. Um,
Yeah, I was just thinking because you said that this was like the equation for half life, and so it's like if a to the 0 times e to the k to e to the kt equals a to f, wouldn't a to the f kind of be like, if you have like y equals.
yep. Yeah. Okay. I get what you're saying. Yeah, we can basically say it's y. This would be y.
Yeah, I should have said y, not y value.
Um, so because we aren't given a mass, we kind of do this little substitution here. Um, so we know um, that this we're expressing this as a half-life, and what we defined a half-life is the um, basically the how should I write this? Um, yeah, so A0 divided by AF is going to be like half, basically, because it's a half-life.
Mm-hmm.
So this is kind of saying that when it starts, it loses half its mass when it goes to, it's in its final position. So basically, how we write this is um, we say that AF is equal to A0 times 1/2, and then we just substitute AF. So it's 1/2 times A0 is equal to A0 times e to the kt, and we're going to cancel out the A0. So all that to say is since we don't have a mass, we're just going to say it's half-life, so the ratio between these two is half. So then we have half equals e to the kt. Okay, now we're trying to find k, basically. So k is how do I kind of explain this? It's basically a special number that each kind of substance has, because each substance is going to have a different half-life, how it, crumbles down. So K is kind of like a special constant for each substance that mirrors that change. So basically, what we would do is we know that our T is 5,730, so we can go ahead and replace that, and we'll leave T in years. Sometimes we'll need to convert it to like seconds or hours or minutes or whatever, but for now we'll
Mm-hmm.
just leave it as T. So we have 1/2 is equal to E to the K times, oh, not 3, 5,730 years, but I'm not going to write that. Okay, so now we're trying to solve for K. So how can we do that?
Mm-hmm. Um, I mean, I guess you could just like put it into the square root, but it would just be like a to the 1, I guess. So it would be if you made it into I'm not sure how helpful this would be, but it would be turning e into a square root, but it would become like square root of k to the
How are you turning it into a square root?
with the what's the function the property's name, like the fractional exponent rule or something.
Um, Fractional exponent rule.
Can you do a square root of 1?
Um, you can, but I'm pretty sure that just means like it's that number. So like, if we write a square root, we can write
So it
this
would
as
basically just
one
make it the
half.
exact same, so it wouldn't do anything.
Yeah, so square root of 1 would be a 1/1. Yeah. So what if we use, if you remember, so we're trying to isolate k. Um, there is that one weird property that we use with fractions sometimes, where we take b to the log b of x, and this is x.
Oh, so you need to do. Okay.
Yeah. So if we take the natural log here, we're
Because
gonna get k back into like the floor. It's not stuck up in the ceiling. It's not in the attic. So if we take the natural log of both sides, we're gonna get natural log of 1/2 is equal to k times 5,730.
mm-hmm.
All right, what's the last step?
You divide 5,730.
Yep, exactly. So k is equal to natural log of 1/2 over 5,730. Okay, now if we want to write this as like a graph function, we basically say that the y as like our final substance is equal to the amount of stuff we initially have times e to the natural log of 1/2 over 5,730 times however much time we have.
Mm-hmm.
And this is our answer. Because it asks us to express it as a function of time.
Yeah, it doesn't look like a pain at all.
No, it's not too crazy. It's just you kind of got to know the process. Um,
Yeah. It seems like pretty simple math. It just looks like a really like complicated way to write the answer.
yeah, yeah. So let me. Okay, this is the next problem after this one is kind of funny. It's just like a really large half-life time. So, um, so this is the problem that I'm gonna have you do, but I'm gonna change the half-life number so you're not spending quite literally 80 million years writing it. So we'll change this to 800. That's gonna be the only difference, and that's just to save us some time.
Yeah.
All right.
Okay.
So same kind of problem. We're trying to
Mhm.
write it as a function of time, and we haven't been given the k yet, but we are given an initial time
Mhm.
period for the half-life. So what should we do?
So the formula is A of F is equal to and you said you can basically just plug this into as so it's 1/2 times the A of 0, which is
Yeah, I kind of wrote it. I wrote it out all the way. The the kind of quick explanation is that if we divide a to the 0 over, AF divided by A0 is 1/2, because that's
okay.
how
Yeah,
we
because you
understand the
spend it. Yeah.
definition. Yeah. So you don't have to write it out like 1/2 A0 the whole way every single time. I just wanted to show you the
Mhm.
whole process.
Right. AF. And I'll just point an arrow and
Yep.
cross that out because that'll be faster.
Yep. Totally fine.
So it's 1/2 is equal to e to the k to the 800.
Mm-hmm.
And then you do the natural log, and then you just divide the 800 over.
Yep. And yeah, so go ahead and do that quick. I'm gonna find the next problem we're gonna do because we're gonna change things up a little bit.
I don't really remember how to write the equation though.
Okay. Um. So we're gonna take the natural log of both sides.
Mm-hmm.
So that means both of these. I'm gonna give this a little bit more room here. So we're basically gonna take natural log here, natural log here. So what happens to this side?
They cancel out and the k comes down.
Mm-hmm. Yep, so go ahead and write that.
I'll just write it, I guess, to the right of it.
Yeah, you
Or no,
can write it.
I can probably write it below.
Sure, however you want to do it.
All right, no, hold on. Or it's just divided. I really don't have room. I should have.
That's okay.
It'll look a little weird, but it's technically correct.
Yep, and then if we were to put it into a function, we'd say y is equal to a0 e to that number times t. You get the idea, right?
Mm-hmm.
Okay, so the next problem we're going to do is... Okay. So let me... Should I write this? Okay, so we're going to use carbon-14, which is the substance we used just before this. And we got k is equal to natural log of 1/2 over 5,730. Okay,
Okay.
so if we have this substance, so and let me actually grab the problem. Okay. So we find a bone, we're an archaeologist or something, and the bone has 20% of its original carbon-14. So if this is the carbon-14K, how old is the bone? So what is this question looking for?
Um. So it's basically taking the time it takes to reach the half-life, and it's like showing you like almost like the ratio, but I don't know, that doesn't feel right. But yeah, the time it takes for it to reach the half-life, and then from there you're inferring how long it would take to reach 20%.
Exactly. No, you got it. So, and you were saying the ratio, that's correct. So A over A0 is 20% basically.
Mm-hmm.
So instead of it being 1/2, it's 0.2. E to the kt, I'm not going to write out all of k. Um, but yeah. Wait, do I have this right? Well, let's see. I might have this wrong, but I think this is right. So, all right, so we're at 0.2 is equal to EKT. We know what K is. So,
Mm-hmm.
um, how would we solve this all the way?
Well, I feel like you have to do a natural log
Mm-hmm.
to get the E out. So it'd be um natural log of 0.2 is equal to k, which is that's a whole thing. And then can you put an e at the bottom to cancel out the natural logs?
I mean, you could, but what's going to happen is you're going to shove these numbers back into an exponent, and then you're going to have to take the natural log to get them out.
Okay, so just keep it like this.
Yep. We could. Yeah. So actually, before I say that, what should we do? We're trying to solve for t.
So you have to, I guess, multiply this number over.
Yep. Exactly. And that's going to look like, I'm going to write it all the way out over here. Natural log of 0.2 over natural log of 1/2 times 5,730 is equal to t. All right. So go ahead, put this in your calculator if you've got one, and tell me what you get, or if you don't have one.
I have one. Just give me a second. I have to type the thing out.
Yep.
So it's just like a really large number. 13,304.648, I guess we'll say.
Yep. Yep. Exactly. And yeah, I mean, bones are pretty old, aren't they? Yeah. So, I mean, this is literally the technique scientists use to, figure out how old things are. Um, Literally the same math. Of course, they have, different tools so they can actually figure out how much carbon is there and what kind of carbon and stuff like that. But that's the idea. Okay. Um, what else? Okay, let's stay on this current. We won't move off into new stuff yet. Okay, I'm going to give us a new problem. This, okay. So after 8.3 hours, the substance has doubled.
Okay.
The bacteria has doubled. We want to find K basically. So this will work. Okay, we're good now.
Okay. Yeah, the 15,800 thing was like confusing me, but I think I get it. Okay, so it would end up being Natural log of 1/2 divided by 8.3 is equal to k.
Yeah, close. So, um, so remember, so we're not doing exponential decay, we're doing exponential growth, right? So it doubles in its substance. So instead of it being 1/2, it's going to be
It would
2.
be 2. Okay.
Yep. But then, yeah, everything else is, same idea. Natural log of 2 over our time, 8.3 hours is our k. And then we can use that to do stuff. Okay. Yes, that is correct. And yeah, so that's basically all the new stuff I'm really gonna introduce. The next round of stuff is gonna be there's some cooling, so temperature. We get into the carrying capacity. So the LD50, I'm sure we'll see a little bit of that when we do our work.
Mhm.
Um, and that's basically going to be our next steps. Okay. So how does Half-Life feel? Does it seem all right?
Yeah.
Okay. Then, yeah, I think we're good to call it here. A couple minutes early. Um, like I could give you more problems, but it's just going to be,
Yeah, it's
busy
just kind of
work.
repetitive at that point.
Yeah. Okay. Cool. Do you have any other questions, or we good?
No, I think it's okay.
Okay. Cool. I'll see you next time.
Yep. Thank you.
Thank you.